All right, good afternoon or good morning, whenever you're watching this video. I just wanted to try to test this out, and we're going to do a little bit of practice today on section 2.1 and 2.2. So concepts in 2.1 we're going to be doing is talking about increasing, decreasing, constant in functions, and where there's a relative max or a minimum of a function. And we're also going to be looking at some piecewise functions today. Some vocabulary. We want to look at this visual of what it means to be increasing. All right, so if it's increasing from left to right, it's going up. So on this interval right here, you want to say that that is increasing, okay? Now, if it's going down from left to right, we're going to call that decreasing. Now, you don't want to include the endpoint. So if you notice right here, they are using parentheses and not brackets, okay? So we're decreasing on this interval, and then we are increasing on this interval for that function. And notice the last example is called a constant. There is no up or down, it's just straight across. That's called a constant, okay? All right, so now this is the formal definition from your textbook. The formal definition says that if a function is said to be increasing on an open interval, that just means not including the endpoints, for all a and b, such that a is smaller than b, so you're traveling in your x values from a to b, it implies that f of a is going to be smaller than f of b. So if we're going from left to right, from a to b, you're going to go f of a to f of b. It's going to be increasing, okay? Now, what would I change in order to make this say decreasing? I would just need to change one thing, okay? Well, two words. It's said to be decreasing on an open interval from a to b. So we're still traveling from left to right, okay? Still traveling from left to right, but it's going down. So f of a is going to be bigger than f of b, okay? All right, so here is an example. It's a piecewise function. So we're going to determine if the intervals on which the function is increasing, decreasing, and constant. Okay, so where is it increasing? What open interval is it increasing on? What color do we use up here? Yellow. Let's go with yellow again. So the open interval that it's increasing on is from here. It's going up and to the right. I think that's the only place. Yeah. So it's increasing on the interval from 1 to 4. Now we're not going to include the endpoints. Where is it decreasing? It's decreasing on the open interval from, it's going down and to the right here and right here. So it looks like it's going down from the interval -1 to 1. And 4, and it's continuing on to the right, so it's going to go all the way down, all the way out to infinity. And where is it constant? So it's going to be constant right on that horizontal line, right on the left. Now from left to right, I would list that from -infinity to -1. Okay, now don't include the endpoints now. Even though it's filled in, it's not changing at the endpoint. It's changing from point to point, every point in between, okay? Just not at the end. All right. Okay, now we're going to talk about relative maxima and minima. So if something is a maxima and it's relative, meaning within that area, there is a point at which it peaks out like a mountain. And if it's a relative minima, that means that there is a bottom, so a trough or a valley, okay? So, and I mean, if you are to report the maxima or minima, you want to make sure that you give the y value, okay? And then you would say at the x value. So it occurs at the x value, and the actual minimum or maximum value would be the y value, Okay, so here in this example number 2, the maxima would be right over here, the 2.370, and it would occur at x equaling negative 0.667. 2. Okay. Oh, how did that 0 get there? Delete that. All right, and then the minima is the y value is 0 at the x value 2. Okay, so pretty straightforward, not super technical there. Just remember that it's called relative maximum or minimum because it is in that area. So notice that this function has arrows on either end. That means it's going to continue to go up, which means it has no absolute maximum. And it's going to continue to go down, which means there's no absolute minimum. But there are maximums and minimums within those areas. All right. So now we're going to look at piecewise functions using different output formulas for different pieces of the domain. So write an equation for each of the functions graphed below. Now this is very challenging for some students. So if it's hard for you, bear with me. Hopefully it'll get easier in a second or in a little bit. We're going to keep practicing piecewise. Okay, so this one is considered piecewise because I have technically 3 pieces, but I'm only having 2 functions. So I don't need to list 3 functions because notice this line is going straight through. It's a horizontal line. So we don't need to worry about that as a separate function. We can just list it on those 2 domains. So the first function that we can list is that line, which is -1, y equaling -1. And then for the x values, the x values can be from -4, -4 to 0. And then we, not 0, sorry, -1. And from 2 to 5. Okay. And then the other function that we have is this horizontal line again. What is that y value? That's 2. Oops. And then that would be for the x values from -1 to 2 with brackets. Okay. Looking at this next piecewise graph, we have 2 separate functions. So I'm going to give it a bracket with 2 different functions. So the first function, this one's easy, straight line again, and it's going through the y value 1, but it's only going up to the x value -1. So the function output is your y value of 1, and then the x values it's going to work on is from -infinity to -1. And then the other function that we're looking at is a parabola. And that parabola is shifted down 3 units. So it would be x squared minus 3. And that is on the x values from, let's fix this. -1 on the first one is a open circle. So I should have a parentheses. This one on the parabola is a closed circle. So I should not have a parentheses, I should have a bracket. And then it's going all the way to +infinity. Okay? I do not need to make curly brackets on both sides of my piecewise function. The left-hand side is enough. All right, so now we're going to practice graphing piecewise functions. So if we look at this example, we're going to graph the function x squared and the function 2x plus 1. What I would recommend is you just graph them both and then you erase it on the places where you don't want to have that x. So x squared, let's graph that one first. If you ever have trouble with graphing any of these, you can always pick a point and plug it in. So the graph for x squared, I'll put in blue, is a parabola that looks like this. 2 squared is 4. It's gonna go up and curve just like that. Okay. So now we got 2x minus 1, that I'll do in red. 2x, plus 1. So it's going to start at 1, and then it's going to rise to run 1, like up and to the right. Now I could go down and to the left, but I'm going to just stay from there. And why am I staying from there? Because I already noticed that this piecewise is going to be for the x values smaller than 0. This is going to be the blue line, sorry. And for x values that are greater than 0, I'm going to make that the red line, okay? So smaller than 0, I'm going to erase this, these blue values, okay? Now I actually have to edit this blue right here to be an open circle, okay? And then the red line is going to be the rest of it on the right side. Everything that is 0 to the right. So notice that it still passes the vertical line test. It does not intersect in more than one point at every input. So even at x equaling 0, notice only the only output is at 1. So that's still considered to be a function. Okay. All right, now we're going to move on to the next section, AT&T. So funny story, when I went to Disneyland last year, I used all my data and it charged me $15 each gigabyte over my data. So that's why this little example came up, okay? Let C of D represent the monthly cost in dollars for using D gigabytes of data. So AT&T charges a flat fee of $50 per month for 5 gigabytes of data. Now if we go over 5, you got to pay $15 per gigabyte of data. Okay, so what is C of 3? Well, 3 represents the gigabytes of data. We are going to be using 3 gigabytes of data. Now what is the cost that we're paying for 3 gigabytes of data? Okay. So go ahead and figure that out. Think about it a little bit. I will pull up my pen color here. Let's do purple. All right. So C of 3 is the cost for using 3 gigabytes of data. And in this case, it looks like we are paying $50 flat fee for 5. So C of 3 is still going to be $50. Okay. Now what's C of 8 going to be? Now that's a little bit harder because C of 3 is going to be 50 all the way up until C of 5. So C of 8 is equal to C of 5 plus 3 gigabytes over, and that's at $15 per gigabyte. So that's going to be 50 plus 15. I don't know if I should be using this notation. I should say 50 already. And that equals, what is that going to be, 95? $95. And if you were in my shoes to use 1 more gigabyte of data when it was about to reset the next day, it was a little bit of a pain. But now we're on a prepaid plan, so it's not a big deal. Our data rolls over, which is kind of nice. All right, the next question is saying, sketch a graph of the function. So this is part of a piecewise section. So I want us to think about this as a piecewise function. It is not quite a piecewise because it's kind of like a step. Well, I guess you could consider that a step function, but I'm going to make it a linear function, okay? So at 5 gigabytes of data, here's my gigabytes, okay? I'm paying $50. Okay, so all the way through to 5, including 5. Now my hand keeps grabbing the screen and moving it, so I apologize for that happening. All the way up to 5. Now, am I still paying for 50 bucks at 5? Yes, so that's why I put a little dot there. Now, at 6, I'm going to be paying, we can make this a step if you want. At 6, I'm going to be paying an additional $15, which is going to bring it up to 65. So from 5 to 6, all the way up to 6 gigabytes of data, I'm going to be paying 65. And then it's going to do the same at the next step, and so forth. Okay? Now, what do I mean by making this a linear function? Well, it could go like this if I just added a straight line to that. We could see that line. All right? Now, to write the formula for C of D is kind of challenging, but if we want to try and use the lines instead of the step function, the first part of my line is this straight line. Okay? Now that is 50. And then you would say for the x values between, including 0 to 5. Okay? Now, how do we get the next line? Now, you can think to yourself, well, if at 6, what am I going to do to calculate 6? Well, it's really 1 gigabyte of data more. And then at 7, it's really 2 gigabytes of data more. So what am I doing to get the 2 and the 1? I'm subtracting it from the 5. So the original function is 50 plus the gigabytes of data. Okay, so if I did 7 gigabytes of data, I'm going to take that D and subtract it from 5. And then charge $15 for every one of those. So I'm going to times that by 15. Okay, and that's from the values that are greater than 5 to infinity. Okay. Now we're assuming that the data only comes in integers. So that's why we have this step function of integers. We don't have to worry about that so much in this class, but the piecewise part of it is the big takeaway. Okay. So mathematically, let's suppose you could afford to spend no more than $75 of data on a given month. How much data can you use given this amount? Now, algebraically, we can solve it algebraically, but let's just think about it, yeah? So I can't go over 75. So at 50, if I add 15, that's already 65. If I add another 15, that's going to be 80. So I can't go more than 6 gigabytes of data, okay? Now, if they're charging you like parts of gigabytes, then you can solve this algebraically. So you're really going to solve for D when the C of D equals 75. So if we wanted to do that, you would use the second part of my piecewise function. So I would do C of D is 50 plus this one, 15 D minus 5. So I would put 75 here and then solve for D. So 50 plus, and you can distribute that. That would be 15D minus 75. And so forth. So you can continue to solve for D, which in this case would give me probably some value between 6 and 7, because 7 is bigger than, 7 is going to be 80 bucks. Okay? So if that's the case, then and you work it out, then you're probably right. All right, so now we're going to move on to section 2.2, the algebra functions. The algebra functions are pretty straightforward. What it's just saying is if you look at a graph and you got two functions and you want to add them, if you want to divide them, if you want to subtract them or multiply them, you can do that, okay? You just multiply the outputs or you add the outputs and you divide the outputs. Now you have to just be careful with division. What can we not divide by? If your output is 0 and it's in the denominator, then you would say undefined, okay? So this is the same as saying P of 1 plus H of 1, okay? That doesn't mean times, okay? These are functions now. This doesn't mean P times 1. That's P of 1. So what is the output at the x value 1? So here's 1. Here's my P graph. The output is 2. And for my H graph, the output is 3. So this would equal 2 plus 3, which is 5. Okay? Now, if you were doing the class with me, I'd say pause right now, press pause on the video and do the next 4. And then press play after you've done the next 4. Okay, pause it right now. I'm going to continue. So when you guys hit play again, you'll get the answers. So the next one's h of 0 and p of 0. So p of 0 is going to be, here's 0. And I got this output of 1 on my p graph, 2, 3, 4 on my h graph. So it's 4 divided by 1, which is 4. Not bad. I don't have anything crazy there. H of -3 minus P of -3. You see how I'm doing that? -3 is inside, and I want to minus the 2 outputs. So be careful, the order matters here. So -3 is 1, 2, 3. Here's my -3. And here are my 2 outputs. So the first output is going to be -5. And the second output is going to be 4. So this is going to give me -9. Okay, and then the next one's multiplication. So this is P of 1 times H of 1. P of 1, oh, that's the one we did right above on A. So that'd be 2 times 3, which is 6. So slightly different, just the operation of multiplication and not addition, as in example A. And the last one we're going to do is P of -2 over H of -2. And P of -2 is right here and here. So we got 3 divided by, oh, there it is, 3 divided by 0. So what more can we say for this one? It is undefined. Okay. So this is using the algebra functions, and we're looking at them graphically. All right, so in the next section in your handout, we want to now look at them algebraically. So if I'm subtracting 2 functions, you can put them together and just put a minus between them. So this is f of x minus g of x. Okay? Same like b, this would be f of x divided by g of x. And then the last one is evaluating and subtracting. So this would be like f of 10 minus g of 10. So go ahead, press pause. I'm going to press pause on my end, and then I'll have the answers revealed after you hit play again. All right, check your answers. The first one should be the square root of x minus 3 minus 8x. Now we have to remember to distribute that minus, so it's going to be a minus 5. The second one is the square root of x minus 3 all over 8x plus 5. And the last one you can evaluate, so you plug in 10 for both functions, and don't forget to subtract that 5 as well, so it's going to be minus 85. Okay, so this is solving, well, combining 2 functions algebraically. So above it was graphically, now this one is algebraically. All right, so now this one is just a try to see, okay? So we got A, B, C, and D graphs, and you don't need to know these graphs at all. I just want you to think about what the combined graph would look like if you added them together. So we'll have here my f of x graph on the top. That's your straight line that's going up and to the right. It's increasing. And then I have my g of x graph, which is this squiggly line. And if any of you are familiar with it, that is the sine graph. And that is bouncing up and down. It's going up like a wave. So if I add the function that is increasing to the function that is a squiggly line, what would that look like in the end? Well, you can do it multiple ways. If you know the 2 functions, you can figure out what it would look like. Or you can like pick points and add those 2 outputs together to get your new output. So I'm going to give you a moment, and I want you to choose which one, A, B, C, or D. Which one of these would work, and maybe test a point to see that that is the right graph. Press pause. All right, so what I'm showing you here on this original graph are red dots. And why did I choose those? Well, you could add the outputs together very nicely. So 0, 0 f of x and g of x have outputs of 0. So if I add those together, I should have 0 as my answer. So I could easily eliminate a. You see how that output is not at 0, okay? Now I can look at the next dot, maybe this one on the right. So at x equaling 3, I have the outputs 3 and 0. And I add those together, I'm going to get 3. So which of these have an output of 3 at 3? 1, 2, 3. This one's there. This one does not look like it's there, so I can cross that one off. And this one also doesn't look like it's 1, 2, 3, 1, 2. Oh, a little bit too high. Right there. So I can cross that one off too, but let's just make sure that B is our correct graph. Let's pick one more point on there. If I add these two values to the left, it's 0 and -3. That would end up with the sum of -3. So at -3, I should also have -3. And those points all work. So B is my combination of those two functions. Now, when you add them together, can you kind of see those two functions being pushed together and kind of it's going up and to the right, and it's also waving. So I think that's kind of cool that you can see it graphically as well. All right, the last thing on this handout for this section is looking at intersection of functions. So whenever you're adding, subtracting, multiplying, or dividing, anytime you combine functions, you want to remember that the new domain has to work for both of those functions. It can't just work for one, it can't just work for the other, it has to work for both. So that is called where the two domains intersect, okay? So when it says it needs to work for both, it is the intersection. And the symbol is the upside down U, okay? So when we did it before, we used the regular U. That's union. That's not the intersection. That means it works for all of those values on all of those domains, okay? Now the intersection has to work for both. So the other thing that we want to keep in mind is anytime you combine two functions where the denominator is there, like this g of x, we got to be careful, yeah? What do we not also want to have happen there? We also don't want g of x to be 0, okay? So if your output is 0 in the denominator, you have undefined right there. So the new domain of those two functions would be the intersection where they overlap, okay? And you need to only list that place. And then also consider the denominator to not be 0, okay? So for example, if I'm drawing domains here from -3 to 10, and then I have the other domain from 0 to 50, okay? Where would the union of these two domains be, okay? The union would be where they overlap. So here's from here all the way to there. Actually, not where they overlap, where they exist on all. So the new domain would be from -3 to 50. And it would be all of these values. Okay? Now, be careful that in this case, our domain is all parentheses. So it would be from here to here, not including 50. Now, if I say, where is the intersection? So you see this symbol is a little bit different. I would have those two same graphs, and from 0 to 50. And the intersection is only where it exists for both, okay? So where does it exist for both? They would only overlap right here. You see right there? So my new domain would be only from where? From 0 to 10, okay? Right there. And it would be still parentheses because it doesn't exist at 0 and it didn't exist at 10 on either of those lines. So that's what you want to make sure you list as your new domain, only where they both overlap. And that concludes our video for 2.1 and 2.2. Join me for the next video on 2.3. Good job, guys.